How to debug hardware with software tools and embedded C. Imagine you're trying to find a tiny glitch in a complex electronic system. You have the software tools, but how do you connect the dots between the code and the hardware? That's what we're exploring today. When working with embedded C language on microcontrollers, debugging hardware issues can feel like solving a puzzle. The good news is, there are practical tools and methods to make this process easier and more precise. First, many microcontrollers support on-chip debuggers. These are hardware interfaces like Joint Test Action Group or Serial Wire Debug that connect to your development environment. Using an integrated development environment, you can set breakpoints, step through your code one line at a time, and watch variables change in real time. This helps you identify if your firmware is configuring peripherals correctly or if there's a register misconfiguration causing hardware malfunction. Serial debugging is another common approach. You can insert print statements in your embedded C code that send messages over universal asynchronous receiver transmitter. These messages tell you what the program is doing at specific points. For example, if a sensor isn't giving expected data, serial output can confirm if the code is reaching the sensor initialization or data reading sections. It's simple but effective, especially when hardware breakpoints are limited or unavailable. Toggling general-purpose input-output pins is a straightforward way to trace events. You can set a pin high or low at certain points in your code. Using an oscilloscope or LED indicators, you can see if specific functions are running or how long they take. For instance, toggling a pin when entering a function helps verify that the code executes as expected and can help measure how long certain processes take. Logic analyzers and oscilloscopes are hardware tools that work hand in hand with software debugging. Logic analyzers capture multiple digital signals at once, decode communication protocols like I2 or serial peripheral interface, and show timing relationships. Oscilloscopes visualize signal waveforms, helping you spot noise or interference that might disrupt hardware operation. These tools, combined with software, give you a detailed picture of what's happening inside your system. Implementing Watchdog timers in your embedded C code is another way to catch system hangs. These timers reset the microcontroller if the firmware stops responding. If your system resets unexpectedly, it could be a sign of a deadlock or a bug. Monitoring these resets helps you pinpoint problematic code paths. Inspecting memory and registers during runtime is also vital. Using your ID's debugger, you can view the contents of RAM, flash memory, and peripheral registers. Comparing these values with datasheet specifications helps identify misconfigurations or corrupted data that could cause hardware issues. Emulators and simulators are software tools that mimic your hardware environment. They let you test and debug your code before deploying it on actual devices. This approach saves time and helps catch hardware interaction problems early, especially when hardware is not readily available. Finally, writing defensive code with error checks and testing modules incrementally simplifies troubleshooting. Isolating hardware interfaces and firmware functions reduces complexity and makes it easier to find faults. Combining these software debugging methods with hardware analysis tools creates a comprehensive approach to solving embedded system problems. So, when you're working with embedded C on microcontrollers, remember that a mix of on-chip debugging, serial communication, pin toggling, hardware analyzers, watchdog timers, memory inspection, and simulation tools can help you track down hardware issues efficiently. It's all about connecting the software signals with the physical signals to see exactly where things go wrong and fix them quickly.